Hello everyone, my name is Sarah Ramsey. I'm a member of the Lit Lion Chemicals team. My team members, Brian Clappett, Alexander Hatza, and Daniel Cordova, along with myself, will be talking to you about the design of our natural gas to methanol plant. In order to do so, we will provide you with some background information, we'll take a look at process specifications, and we'll also examine economics and make some recommendations. Let's start with background information. Our plant is located in Philadelphia, Pennsylvania on the Delaware River. This is an ideal site location because it provides us access to rail and ship transport. There's also an abundance in skilled workers, which gives us the flexibility to hire the best of the best. Our plant culture takes quality and safety very seriously. We strive to provide our consumers with high-quality products and in timely fashion without jeopardizing the safety of our plant workers. Moving on to process specifications and overview, we were provided a feed at 400 pSIA, 80 degrees Fahrenheit, and a flow rate of approximately 50,000 pounds mass per hour. The specifications we had to meet was creating a methanol product that was at least 99.85% pure methanol at a flow rate of at least 71,000 pounds mass per hour. Our team was able to successfully meet both of these specifications, providing a methanol product with purity 99.86% pure methanol at a flow rate of approximately 79,000 pounds mass per hour. Here's a quick overview of the process. You start out with the natural gas feed, you go into a reforming unit, followed by a methanol synthesis reactor, and finally distillation before you have your finished methanol product. In our case, it was a little bit trickier because we had hydrogen sulfide and mercury present in our feed. Mercury and hydrogen sulfide are both corrosive and can decrease the efficiency of the plant. Hydrogen sulfide can also cause catalyst poisoning, which can further decrease the efficiency. As a result, we created two other units, a mercury removal unit and a main treatment tower, to get rid of these. Then we followed them by a pre-reformer, which broke down the larger hydrocarbons into smaller ones, which was then fed into a reformer unit, which created syngas, going into the methanol synthesis reactor to make the methanol, followed finally by distillation in order to achieve the high purity methanol product that we used. Now that we've seen a quick overview of how to achieve the high quality products, let's take a look at safety. A lot of the chemicals used in our plant are highly hazardous. The four we deem most hazardous are mercury, hydrogen sulfide, methanol, and methane. Mercury is a highly toxic compound. It can be leaked into the environment through faulty unit design or improper disposal techniques. The leaks can affect the quality of the air as well as the other bodies of water surrounding it, affecting the lives of humans as well as aquatics. Hydrogen sulfide is a highly toxic and corrosive compound. It can react with moisture in the air to create sulfuric acid, which is even more corrosive. Hydrogen sulfide has also been linked to the smog events, leading to illnesses and death of many people. Methane is a flammable greenhouse gas with a global warming potential 20 times that of CO2. Methanol is a highly flammable compound and is also considered a volatile organic compound, or VOC. VOCs have been linked to increased irritations, cancer, and increased emergency room visits. Therefore, all of these chemicals have to be handled with care, and we took a lot of these things into consideration when we were making our plant design. Finally, everyone who is on site is required to wear the proper personal protective equipment at all times. Now I'll hand it to Dan to talk about his BFDs.
So now I'll be talking about our base case flow diagram for our process. The major equipment in our process consists of a mercury removal unit and a mean treatment tower, 3 reactors, a set of vapor liquid separators, and 2 distillation units. The process can be broken down into 4 different sections. The first section is a mercury and sulfur removal. Then we have steam reforming. After that comes methanol synthesis, and then at the end we have our methanol product purification. In the first part of our process, the natural gas feed is treated to remove mercury and sulfur impurities. Natural gas feed first passes through the mercury removal unit where the mercury is removed. As Sarah mentioned previously, mercury could damage our equipment in the downstream process. Thus, this is why we decided to place the mercury removal unit first to limit equipment damage. After that, we have the amine treatment tower. The amine treatment tower utilizes amines to convert sour gas to sweet gas. In this case, we decided to use MDEA because MDA has higher affinity to hydrogen sulfide, which is the impurity that we're trying to remove. Additionally, sour gas is a corrosive, and sulfur could poison the reforming catalyst in the downstream process. In the second part of our process, the sweet gas from the amine treatment tower and steam are fed into a pre-reformer, where heavy hydrocarbons are converted into syngas. The purpose of the pre-reformer is to increase the overall conversion in the steam reformer reactor, which is our next unit in the process. In the steam reformer reactor, we have further conversion of hydrocarbons into syngas. A vapor-liquid separator is located after the steam reformer reactor in order to separate a large portion of the water so that it can be recycled. In the recycled steam, we also have a purge where we purge out some water to be sent out to wastewater treatment. The vapor outlet stream, which contains syngas and some of the remaining water, is used in the next part of the process. In the next part of our process, the syngas stream goes into the methanol synthesis reactor, where it is converted to methanol. After the methanol synthesis reactor, we have a second separator. The purpose of this separator is to separate out the lighter gases out of our liquid stream. The liquid stream contains our methanol product, which is sent to the distillation column to be purified. The next part of the process is the purification. In this part, distillation towers separate out the methanol product from water and some byproducts. The distillate of the columns contains our product, and the bottoms contains water, mostly water, and some byproducts. The methanol product from the distillates from both columns is combined and is sent out to a methanol storage unit. On the other hand, the bottoms, which contain mostly water, are sent to wastewater treatment. Now I'm going to pass it on to Brian, who is going to talk about our economic analysis.
To begin the economic analysis, we could break it down into both initial capital and then annual operating costs. The initial capital cost can be broken down into IBL and OBL costs. IBL, which is the inside battery limit costs, are typically things such as equipment, while the OBL are things such as site development and product storage. The annual operating costs are things such as our raw materials, our utilities, and our fixed costs. Some raw materials we will be having will be water and natural gas, while utilities we will have our electricity and other steam. To estimate the IBL capital costs, we could break it down into 4 different regions: your reactors and towers, heat exchangers, expanders and compressors, and separators. As you can see here, the expanders and compressors take up the largest chunk of the IBL capital estimate. But we found this by utilizing the Aspen Process Economic Analysis software. The total cost for this was approximately $34 million. To then look at the OBL capital estimates, we can also break those down into 4 things: the site development, the utilities, the raw material and product storage, and the environmental. All of these are crucial when designing a plant. This ensures the site is capable of withstanding the operation by site development, upgrading the utilities, installing product storage tanks, and considering wastewater production. These values were obtained by scaling historical data for inflation to our fiscal year. The largest contributor to the OBL capital estimate costs was the product storage. The total OBL costs for the plant are approximately $62 million. To analyze the annual cash costs, it can also, once again, be broken down into 4 things. We have our raw materials, our utilities, our wastewater, and our fixed costs. The natural gas feed is the greatest raw material cost, while the greatest single utility cost is the operation of the refrigerant. Finally, the greatest single fixed cost is the property tax. Utilities are the greatest contributor to the annual capital costs as a whole. An economic analysis was performed on these values to relate our cash costs to the price of product. The cost values were normalized per pound of product. That way they can be compared to the our sale price of our product, and allowed us to calculate how much we're going to get back operating as per our product rate. At our current cash costs, they're approximately 9.5 cents per pound. With the price of methanol at 12.5 cents per pound, we're getting an approximate return on capital of 3%, 3 cents per pound. A cumulative cash flow model was constructed to monitor the economics of the plant over time. Here, the startup costs, which is the blue region, represent when we are just starting up, the capital costs. And the operating years show an upward trend, showing that the plant does make money on a yearly basis. However, with the inflation over time for our plant, the net present worth of lifetime is negative $13.1 million. Therefore, our plant will not make money over time. I'll be passing it off now to Alex to talk about some sensitivity analysis we've done.
So the discount rate, or ATROR, represents a valuation of future money as present money. So what that means is if you've got an ATROR of 10%, if you want $1,000 in the future, all you have to do is invest $900 now. It's a 10% return. So in terms of taking a look at how the company is performing economically, we varied several economic parameters and took a look at the process's calculated ATROR, after-tax rate of return, to see how it's affected. So the first sensitivity analysis took a look at the cost of raw materials. So the cost of raw materials were varied in terms of cents per pound of product produced. So going to the right, the cost of raw materials are increased, and you can see that the ATROR, the discount rate, is decreasing pretty quickly as those cost of raw materials goes up. Roughly 2 cents greater than the actual cost of raw materials, we see the after-tax rate of return going below zero, which would essentially mean that if you invested $1,000 in the plant, later you would get $1,000 in the plant, and you know that's not what you want. So that ATROR of zero is sort of where the plant starts to go down. The second sensitivity analysis takes a look at the product price as it changes. The product price is 12.5 cents per pound of methanol. So here we decrease the product price to see what it would do to the ATROR, and right around 11 cents per pound of methanol, we see a value of zero ATROR. So our required netback would be above 11 cents per pound of methanol so that we can have some good returns. The third sensitivity analysis takes a look at utility costs. This is much like increasing raw material costs. The trend is very similar. Once again, the process can tolerate roughly 2 cent increase per pound of product before ATROR drops below zero. Now, the fourth sensitivity analysis is a temporal one. This takes a look at schedule compression or delay in terms of construction time. So on the left, you can see what it would look like if the schedule were moved up and somehow the plant were built in only 1 year. On that side, we've got a higher ATROR because the plant starts producing methanol sooner. It can start making money and selling product more quickly. So you're going to get a better return on that. On the right side, we have the farthest data point is a 3-year delay in construction. So that would be 6 total years to build. And you can see that the ATROR has dropped significantly because there's more time where we're spending money and less time where we're making money. The fifth sensitivity analysis has to do with variable sustained capacity of the plant. So for this one, we adjusted the amount of methanol that can be produced in the plant and then accordingly adjusted the cost parameters like raw material costs and utility costs to see how that would affect the ATROR. Here we found that smaller plants would have a lower ATROR and larger plants would have a significantly larger ATROR and positive net present value. This would be a great thing if we were able to accomplish it, but given the fact that we have a fixed feed, we won't exactly be able to implement this into our process. Now, another kind of discount rate is the IRR, the internal rate of return, and this represents sort of the risk of an investment over time. So you'd like your discount rate to be higher so that there's less risk. So that way, if the discount rate reaches a certain height, it won't bring the net present value of the process or company down to zero. This value is calculated from the cash flow. And as you can see, the first 3 years there are negative cash flow as the plant is being built, but the cash flow goes positive once we start selling product. Now, the net present value 12 represents the present value for a discount rate of 12. Now, our discount rate is 7.2, which means that's the highest discount rate we can tolerate. This is the value we've calculated for our process. Now, since the net present value assumes a discount rate of 12, that net present value is going to be negative. So despite our positive cash flow at the end, we've got that negative net present value. And for that reason, we believe that as designed, this process would not be prudent to build. However, despite that, we have a number of recommendations for the process to hopefully help get it on track and continue to be in consideration for construction.
Some recommendations for the project moving forward include researching ways on how to remove the refrigeration unit due to it having the largest effect on the utility costs, decreasing the water needed for the system while maintaining the necessary conversion, as this will help lower the wastewater costs. Also researching new catalysts with better conversion and different operating conditions for the methanol synthesis reactor. Finally, we can run a statistical analysis to supplement the sensitivity analyses, such as a Monte Carlo simulation, to determine if the economic conditions will be favorable to our plant in the future.
So, thank you for watching our presentation today. We hope you'll consider our proposition for this methanol synthesis plant. Thank you.